Let me ask you folks a problem. Okay. All of you have calculators in your mobile phones? So fraction is okay? So suppose this is a sample. Okay? Tell me whether this sample could have come from a population with mean 4 and variance 2. Could this sample have come from a population with mean 4 and variance 2?
So 1 है क्या? 7 है.
What's that?
2 after 2.
7.
So 3 2 so बीच में.
2 and 6. This 7.
क्या है?
That's why I'm going to start a technology from next lecture onwards. It doesn't require me to write anything on the board. So how will you solve this?
X bar minus mu divided by
So first, okay, your null hypothesis
This is a sample or it's a population?
is a sample.
sample.
The null hypothesis mu is equal to 4.
4. Yes.
Yeah?
Yes.
Against the alternative hypothesis,
Mu is not equal to 4.
mu is not equal to 4. Okay?
Yes.
Now, if mu is equal to 4, then x bar minus 4
Divided.
sigma by root n. Right, so let me make this say, just to give you a root, I'll just put it 1, right?
How much is that? 4? 7.
1. Because I don't want to square root, na? Square root 2 है किधर है? 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13. Yeah? This should lie between minus 1.96 plus 1.96, 95% of the times. Yeah? So what do I have? So what is x bar?
3.4.
3 point?
46.
3 point?
446.
3.46.
7 change किया
3.15.
3.15.
3.15.
Data change.
It's 3.15.
3.15.
2.84.
Is equal to what? This whole quantity?
Quantity divided by 50 minus 50.
Another way of creating that quantity is obviously, as you see, root n upon x bar minus q by sigma, because sigma by root n I have taken root n on top. Right?
Minus 50.
Minus 11.
Calculate karo. It can only be one number.
That's 7 by 13 in the denominator, right?
N is 13, no, root n. It has to be root n, isn't it?
No, we have taken root of sigma square.
Yeah, but sigma square upon n. Sigma upon root n.
Sigma upon root n.
So root 13.
Minus 3.05.
Minus 3 point?
05.
Yeah, you're getting minus 3.05? Do we get it?
Yeah.
Minus 3.14.
Minus 3.14.
One by square root divided by this, which is minus 3.0. 060, हाँ 060.
Minus 0.
Minus 3.0.
Minus 3.06.
Outside 3.
So what do you get?
Minus 3.06 or 3.1. Minus 3.1.
0.6.
Now,
Sorry, the denominator is 7 over root 13.
no, 1 upon root 13.
One.
Because standard deviation is your 1.
Okay. I thought it was 7.
1% chance of type 1 error.
Minus 3.06.
Z value corresponding P.
So what you do now do is, say if you look at the distribution like this is 0, this is minus 3.06, this is plus 3.06. Calculate this area and this area. Yeah? And add the two. So if you added that, what do you get? You can do that in R, right?
Yeah.
So you have R. And you know how to do it in R?
Not easy.
P norm.
We'll take some value, large value, and then.
P norm minus 3.06. P norm minus 3.06.
And plus 3.06 for the area that lies.
No, because this is symmetric distribution, so double.
Okay, yeah.
This is alpha by 2, this is alpha by 2. So what's that value?
Answer.
0.001106.
What's the command?
P norm bracket minus 3.06.
Minus 3.06, it is this area.
Yeah.
But I want this area as well.
Into plus.
So 2 into this.
Ah.
What is that?
So 0.00
Point
0.0002.
2. Right? So if if I say that these elephants have not come from this population, there is a 0.002% chance of going wrong. 0.002% chance of going wrong. This is the p value. To get the percentage, you have to multiply it by 100. So decimals will come to the 2 digits, right? So if you reject the null hypothesis, that mu is equal to 4, right? Then I have is basically 0.002. So 0.002% chance of rejecting the null wrongly. Yeah, now whether to reject the null or not to reject at this point is your call. You have to decide what is the cost and benefits of rejecting the null wrongly with 0.002. Right? Okay, so if there are say thousands of elephants that you are going to capture, and say 0.002 elephants means you will really end up capturing some healthy elephants, and no way you are going to have a healthy elephant in your, treat a healthy elephant, then 0.002 might also be too large. Yeah, so it depends on what the call is. Now, there are 2 cases. I have looked at this side and this side. Why? Because if either I am surprised if x bar is too low relative to mu or x bar is too high relative to mu. You see, mu is what I believe. X bar is what I see. X bar minus mu is the gap between what I see and what I believe. and if what I see is too low relative to what I believe, or if what I see is too high relative to what I believe, I'm going to say that what I believe needs to be might not be correct. Right? Sure? So I'm going to be surprised either ways. I'm going to look at X bar and then I'm going to say that I'm going to give up this hypothesis and I'm going to reject this in favor of this. But suppose I was interested not in this, but the alternative was whether mu is greater than 4. So suppose I have a population, I have a sample from that population, my hypothesis is that the sample mean is 4, population mean is 4, and my alternative is the population mean is greater than 4. In which case, observing X bar lower than mu does not give me evidence against this in favor of this. It's only if I see what I see is substantially greater than 4 will I say that the population mean seems to be greater than 4. If what I see is substantially less than 4, that doesn't allow me to say that I will give up the null hypothesis that mu is 4 in favor of the alternative mu is greater than 4. Right, so there are oranges, for example, right, in a box, and my null hypothesis is that an average orange weighs 100 grams, and my alternative is that the average orange does not weigh 100 grams. I put my hand and I pick up orange, it weighs just 10 grams. Then I can say that the evidence that I have got contradicts my hypothesis. That the average orange weighs 100 grams, because I have got an orange which weighs 10 grams. But suppose my null was that the average orange weighs 100 grams against the alternative that the average orange weighs more than 100 grams. Then finding an orange which weighs just 10 grams does not give me support for the hypothesis that an average orange weighs more than 100 grams against the null. In which case the downside is not useful. In which case what I'll do is I'll only be interested in this part of the distribution. In which case what I have is called a one-tailed test. Whereas previously what I was doing was I was using a two-tailed test. Now I have a one-tailed test. Okay?
I have a question. So, when we got negative 3.06, we should have taken only on the left side. Why have we taken
No,
on the right
because
side?
my hypothesis there was alternative mu is not equal to 4. Right? So my null hypothesis was that the average orange in this box weighs 100 grams.
Right.
If I find an orange, if I randomly pick up an orange, and suppose that orange weighs just 10 grams, then that is evidence against my hypothesis. Or if I find an orange which weighs 500 grams,
Right.
that is against an evidence against my null hypothesis that the average weight is 100 grams. So if I find it either too low or too high, I give up my null hypothesis. So it's both ways.
But this negative 3 is because it's negative should. we
No,
should
but so what is the whole idea? That because what I found X bar is what I observe, mu is what I believe. This is the gap between what I observe and what I believe. If the gap between what I observe and what I believe is too large or too negative or too positive, then I am going to say that what I believe seems to be quite unlikely in the light of what I observe. So even if X bar minus mu is either very negative or if it's very large and positive, then I have to give up the null hypothesis. Right, so whether it's minus 3.15 or plus 3.15. Therefore, the probability of going wrong is the area to the left of minus 3.06 and area to the right of 3.06, because I am going to reject my null hypothesis if the test statistic is less than minus 3.06 or greater than plus 3.06, so both ways. But now suppose my null where only mu is greater than 4. Right, so if my null hypothesis, the average orange in this box weighs 100 grams, and the alternative was that this weighs more than 100 grams. Then if I find an orange which weighs just 10 grams, it does not give me evidence against the null hypothesis in favor of the alternative. Right, I can't reject the null hypothesis that the average weight is 100 grams in favor of the fact that the average weight is more than 100 grams. Only if I get an orange which is surprisingly heavier, then 100 grams, to make it very likely that the average weight of oranges in the box is 100 grams, can I give up the null in favor of the alternative? So in which case, I must only look at this part of the thing. Whereas if I have a null hypothesis, the average weight of oranges is 100 grams, and the alternative was that the average weight of an orange is less than 100 grams, alternative, then finding a orange which is heavier than 100 doesn't help me reject the null in favor of the alternative. Only if I find a very, very thin, light orange, do I give up the null in favor of the alternative. Right? Sure?
So sir, what do we do in that case?
So in which case, what we will do is, so all that we will do is we will have a one-tailed test. So if you find 3.06, then the probability of type 1 error will only be this side of the area. This side you will not bother about. If your null is this, then your probability of type 1 error will only be given to the left of this, not this. So therefore what matters, why is that critical? That's critical to help you find out what is the type 1 error. What is the p-value? So that is the whole thing which is going to help you make decisions. Right? So for example, I can have suppose my null hypothesis is that this pair of spectacles will not break if I drop it. And the alternative is it will break. I drop it, it breaks. Right? I drop it, it breaks. Then what I've seen is surprising in the light of my null hypothesis. My null hypothesis doesn't break. I dropped it and it broke. Right? So therefore what I have observed quite contradicts my null hypothesis, and if I do it 10 times and 10 out of 10 times the spectacles break, then probably it's what I found is very, very surprising in the light of my null hypothesis that this survives a fall. Therefore I must give up what I believe. Right? So what I am looking at is this gap between what is I observe and what is there. But suppose my null hypothesis were that if I drop this pair of spectacles, it will not break, and the alternative were that it will break exactly into 8 parts. So suppose it breaks into 2 parts. It does not help me reject the null hypothesis in favor of the alternative that when this breaks, it breaks into 8 parts. Right? So what right? Is that clear? Okay. Another part you must again to look at this construction of this idea. What is the test statistics? Yeah? This is my test statistic, right? X bar minus mu 1 sigma. The larger this is, either positive or negative, the more likely I am to reject the null hypothesis. When will this be large? When X bar, what I observe, is substantially bigger or substantially smaller than what my hypothesis is. But this will also be smaller, larger the sigma. Right? What is sigma? Sigma or sigma by root n. What is sigma by root n? The variability of my empirical observation. The larger the variability of the empirical observation, the smaller is my ability to use a difference between the empirical observation and what I believe as evidence against what I believe. The larger is the variability of what I empirically observe, the less is my ability to use that empirical observation to say that what I have empirically observed does not fit in with the reality, with my hypothesis. Think of it. Suppose you have a weighing scale and the weighing scale is very accurate. In this sense, it has a small half a gram here and there for 100 kilos, right? And so somebody gets a sack and says, this sack weighs, somebody tells me that there is a sack which weighs 150 kilos. I put it on my scale and my scale says 90 kilos, 90.1 grams. Now I know that there is some variability in my scaling, so next time I put it will give me a different number, I put it, but that variation of numbers is very small, it is around 99 some here and there. I can say that, Baba, you have said this weighs 150, but this evidence is saying it weighs only 99, so I am not going to reject, I am going to reject your hypothesis. But whereas my weighing scale were so sensitive and so random that it could weigh anywhere between 0 to 200 kilos. Right, when I put the sack on it, just swung widely. So whatever number comes up there, suppose another number comes, the same number, suppose 99 comes up, my confidence in saying that this is not 150 kilos is quite weak, right? Because next time I put the same sack, it might show 170 kilos. Next time I put the same sack, it might say 20 kilos. Next time I put the same sack, it might say 180 kilos. Right? So, therefore, larger the variability of what I observe, the less is the value of the same gap between what I observe and what I believe. Right? And larger is my M. The larger is my ability to reject a null hypothesis. So sometimes you might not be able to reject a null hypothesis. Right? Sometimes your p-values might be pretty large. But those p-values could be large because your n is small. Because there are too few data points. Right? So one of the reasons why p-values could be small is because you just have too few data points. That's why root n x bar minus mu by sigma is small, and therefore it's lying very close to that whatever value you've got, right? Whatever null hypothesis value that you've got, and therefore the p-value is seeming to be large. So one important decision that you have to take when you're designing a test is what should be n, and the best and the only answer to it is large as possible. As long as all these n's are independently collected. If they are not randomly collected, then this whole idea doesn't make the smallest sense whatsoever.
So what do you mean by randomly?
By randomly collected, x1, x2, x3, x4 must all be independent of each other. How do you ensure that? Technically, random selection means every element of the population must have the same chance of being selected. Yeah? Every element of the population must have the same chance of being selected. So when we decide to choose, for example, households from a village, suppose a village of 200 households, and we have to choose 20 households from there, then what I would do is, I would mark each household, 1, 2, 3, 4, 5, 6, up to 20. Put that in a box, and pick up 20 chits at random with replacement. That would be a random sample, because at each point of time, each chit has the same chance of being drawn. Right? Okay? Sure? This is called random sample. You could have a little bit of a stratified kind of a system. So for example, if you have a village and you might say that 40% of this village are men and 60% of this village are women, and you're sampling, it matters whether there's a difference between men and women. So you might want to say, I'm going to get 200 sample. Out of that 200 sample, 40% will be chosen as men, will be taken from men, 60% from women. But once you've chosen that 40%, so 80 will be men, 120 will be women. Those 80, all the men will have to be given 1, 2, 3, 4, 5, 6 numbers, and then from that you have to draw that randomly. If you don't do that, for example, if you have decided to you want to find out how much a person will pay for a new laptop. So suppose Dell hires you to find out how much people are willing to pay for a new laptop. So what you do is you go to, say, Croma, you go to all the supermarkets and you find people there who have come to buy laptops, right? And you ask them, how much are you willing to pay for a laptop? And that person says, it has this specifications, how much will you pay? Will you be doing a random sampling or non-random sampling? No. Because people who have not come to Croma have no chance of appearing in your sample on that day. Whereas a random sample requires every element of the population to have the same chance of appearing in the sample. So folks who don't buy their laptops from Croma, or folks who don't want to come to Croma or any other mall, right? Okay, are not there in your sample. Have zero chance of appearing in your sample. Right? So that's a random. In fact, this becomes very critical. For example, if you want to suppose you want to do a sample where you want to say find out, you are trying to say set up a health clinic. Suppose you want to start a hospital. Okay, and you want to do a survey about the need for a new hospital. And especially you want to find out how much will the people in this area pay for a new hospital. let's say you're doing a survey. In this survey, so your hospital is a special cancer hospital, right? Okay, so if you do a survey only on for cancer patients about which you will be willing to pay, and how would you randomize? You're not actually randomizing this, because people who are not cancer patients right now are not being included in your sample at all, right? Or if you're trying to find out, say, how many hours does an average domestic servant, okay, so somebody who works as a maid in domestic help in people's houses, how many hours is the average on a domestic worker on an average? Or say, if you think of people who are selling vegetable vendors, you want to find out how much does an average vegetable vendor earn, right? Okay. You can't restrict your sample to only vegetable vendors, because people who are not vegetable vendors have no chance of coming into your sample, right? Okay, and therefore that kind of a sampling design will actually be wrong. Yeah, because your population is not only entirely vegetable vendors. Because you're not asking.
Why would you take vegetable?
So, but if the problem is based around a particular type
Yeah.
of people.
Yeah, but what you're now asking is, that's precisely the problem. See, what's going to happen is, there are some people, okay, so there are some people, so think of vegetable vendors in general, okay. Now there could be some vegetable vendors, some people who are fine enough to be vegetable vendors, but who are not vegetable vendors unless they see that the return from vegetable vending is more than, say, some quantity K. Right? Is more than some quantity K. Sure, I might be a latent vegetable vendor.
Seasonal.
No, I might just be, so for example, I'll be happy to become a vegetable vendor. For example, I'll be happy to be a vegetable vendor if being a vegetable vendor